I do want everyone to kind of see this because this kind of particular thing happens a lot when we are solving differential equations. If you've got the natural log of whatever equal to some function of your variable, so in this case, natural log of y equals to x cubed plus c, or we did the integration. This probably came, this came from like the integral of 1 over y dy equal to the integral of 3x squared. I ignored the absolute value. It's no big deal. We got that. Then we exponentiated both sides. So we got e to the natural log of y equal e to the x cubed plus c. And this part right here is what happens like all the damn time. E to the something plus a constant, we rewrite as e to the something times e to the constant. And then we rewrite e to a constant as a new constant. And apparently Karana likes to use the letter k, so I'll use k. Maybe it's because their name starts with k. Probably not though. It's probably because k is a typical constant letter. So we're gonna do this a lot, and eventually we're going to kind of just like be like, okay, you guys know when you've got e to the x cubed plus c, it's going to become k times e to the x cubed. Right? We're going to make that leap so that we don't have to do this work every time because it gets to be, I wouldn't say annoying, but just repetitive. All right. So I think today it's all differential equations all the time. And so I was trying to find the syllabus for the class, but I couldn't find it, which was disappointing. Because I'm not sure if you guys are going to do first order linear differential equations or not. Either way, today is not the day to talk about them. But what I want to say is, if you're not doing those, every differential equation that we encounter is going to be separable. If you are, then we have these other ones that aren't separable. But so here's what I'll say. Either all your differential equations will be separable, or they'll look this one other way. And if they're separable, that literally just means bringing all of one variable to one side and all of the other variable to the other side. So let me grab some stuff. Where did I put my stuff? Hiding all my stuff. Oh, it's over here on this other screen. Let me bring this over here. All right. Yeah, let's differential equation it up or down or left or right. All right, so let's see here. Where'd you go? There it is. Okay, so solving differential equations. I didn't erase the side. What a loser I am. And we'll definitely try to get into a tank problem closer to the end. Maybe we'll also look at that crazy tumor problem that she was doing at the end of class, because although it is separable, that integral is not easy. I mean, yeah, definitely not easy. So let's look at some easier examples. So let's say you've got something like this. Let's say you've got x squared plus 1 times y prime equal to xy. First and foremost, you typically do want to write your derivative in the Leibniz notation, meaning dy dx or d whatever, right? Whatever your variables are. So I really would prefer to write this as dy dx. And here's the thing. So we're always going to work under the assumption that our differential equation is probably separable. And separable just means, well, separable does mean you can write your derivative as a function of x times a function of y, or again, whatever your variables are. And we totally could do that here. I could, it doesn't make sense to do that, but if we wanted to, we could totally divide both sides by x squared plus 1 and write this as dy dx equal to x over x squared plus 1 times y. But it's not really an important step to note. The real point of recognizing that a differential equation is separable is that means we can separate the variables onto different sides. We can bring all the y's to one side and all the x's to the side. You're always going to want to bring the y's to the side that y is on top on. So if you've got dy dx on the left, you want the y's on the left. You want the x's on the right. And the only operations we're allowed to use are multiplication and division. So I'm going to multiply both sides by dx. I'm going to divide both sides by y. And I'm also going to divide both sides by x squared plus 1. But I really can't stress enough. Multiplication and division are the only things we're allowed to do. You cannot add or subtract. I should say, you normally can't add or subtract. There are some exceptions, like if you're starting off with maybe like y prime x plus 5 equal to 0, then you want to bring, you kind of want to have the derivative on one side of whatever's multiplied by it, and then the other stuff on the other side, and then kind of work with it there. So you can add or subtract, but like not to really separate the variables. I think I have another example that I can kind of, yeah. Okay. So now we want to solve this. So we want to integrate both sides. I should also mention, in case anybody cares, no one should really care, but in case you care, this is a non-autonomous differential equation because dy dx depends on both x and y. Most of the differential equations we're going to encounter are probably going to be non-autonomous. Doesn't really matter what the name is, though. All right, so now we're going to try to solve this. So integrating 1 over y, we're going to get the natural log of the absolute value of y. By the way, the only time you get the absolute value, people were asking this in class, that was good. The only time you get the absolute value is when you actually integrate 1 over something like this, right? If you got a natural log showing up for another reason, there's no need to put an absolute value on it. So that's going to equal, we have to integrate this. So integrating this requires a u substitution. So we're going to do u equals x squared plus 1. Du dx is 2x. 1/2 du is equal to x dx. So this integral here is going to become 1/2 the integral of x dx is my 1/2 du. X squared plus 1 is u. So the integral of that's going to be 1/2 the natural log of u. Sorry, 1/2 the natural log of the absolute value of u. So over here I'm going to get 1/2 the natural log of the absolute value of u plus c. You always want to put the c on the side that is not the side you're solving for, right? So we know we're going to try and solve for y, right? Because y is a function of x. So I'm going to put the c on the not y side because we're going to eventually move it over there anyway. All right, so now we're trying to solve this. So we're going to exponentiate both sides. So we're going to say e to the natural log of y is e to the all this. That's gross looking. E to the natural log of the absolute value of y is just the absolute value of y. Okay, and then I'm going to do a couple things here. Thing one, I'm going to write this as e to the something times e to the c. And the e to the something, I'm going to rewrite the something as, instead of 1/2 times the natural log of the absolute value of x squared plus 1, I'm going to bring the power up here and say it's e to the natural log of the absolute value of x squared plus 1 to the 1/2 power. So then e to the c becomes k, and we have the absolute value of y equal to k times e to the natural log of some stuff is just the stuff. So it's x squared plus 1, the absolute value to the 1/2 power. Okay, and I don't think I gave us an initial condition, so I think we're kind of done. One thing I will say here. So a lot of the times we have these absolute values, and you kind of maybe don't know what to do for them. Most of the time, probably all the time, you can kind of just drop them. And let me kind of show you what I mean by that. So here's what I'm saying. Y is either going to be positive or negative, right? So I should say, first of all, actually, x squared plus 1, always positive. So we don't need the absolute values there. So I can say this is going to give me y is equal to k, sorry, absolute value of y is equal to k times x squared plus 1 to the 1/2. So here's the thing. When you have an absolute value equal to something, and she did this in class, I thought that was great, you either have y equal to that thing or y equal to the negative of that thing. So you're either going to get y equal to k times x squared plus 1 to the 1/2, or y equal to negative k times x squared plus 1 to the 1/2. But here's the deal. You can figure out whatever k needs to be and make it work, right? Like if you end up getting a negative constant, we will find that when we do our initial conditions. If we end up getting a positive constant, we will find that when we do our conditions. So what I'm trying to say in all the words possible is you can pretty much drop the absolute values like right from the get-go. She might want you to show them for a couple steps, but the truth of the matter is you can drop them and then solve for what k is going to be. So let me give an initial condition. Let's say that y naught is equal to 5 when x naught is equal to, sure, let's pick something silly like the square root of 3. Okay. Yeah. So if I do that, so basically I'm going to ignore this one here. Let me pick -5 just to make it a little more interesting. So if I plug in, let's see, I'm going to plug in -5 for y. And I'm going to plug in square root of 3 for x. So square root of 3 squared is 3. 3 plus 1 is 4. 4 to the 1/2 is 2. So I end up getting k equals -5 divided by 2. Which means my final solution is y equal to -5x times x squared plus 1 to the 1/2. So if you have an initial condition and you've got some absolute value garbage happening, really you can just ignore the absolute values. And the reason is because the constant multiple out here will take care of whether it's positive or negative. It's something that I still struggle with. Like, I'm like, oh yeah, we can just kind of forget about the absolute values because we can fix it with the constant. All right, let's look at some more examples. This is from section 7.4, number 14. I got lots of examples. This one is, sure, I'm going to try and make it look funky. So let's say we've got y prime equal to xy times sine of x over y plus 1. Okay. Is this separable? Yes, it's separable, right? Because you can definitely break this apart as x times sine of x times y over y plus 1. Again, I know I want my y's on the side where dy is on top, and I want my x's on the side where dx is going to be on top or not on the bottom. So I'm going to have, let's see, I'm going to multiply by y plus 1. I'm going to divide by y. dy equals x times sine of x dx. We're going to integrate both sides. Okay, the left side's not terrible because you can just write it as y divided by y plus 1 divided by y equal to, okay, the right side is a little terrible. We're going to have to do integration by parts. So we're going to let u equal x, du is dx, dv is sine of x, and dx. And the antiderivative of sine of x is negative cosine of x. So this is going to be, so the integral of x sine x is going to be x times negative cosine x, so negative x cosine x, minus the integral of v du, which is negative cosine x dx. If I have a minus here, I usually change it to a plus. So it's really just plus integral cosine x. And then we can integrate both sides. So integral of 1 is y. 1 over y is the natural log of the absolute value of y equals negative x. I do think your first step when you do integrate, you should have the absolute value, and it's maybe okay to drop it later. Negative x cosine of x plus the integral of cosine is sine of x plus c. Oh, I forgot to mention the initial condition. The initial condition is that y of 0 is equal to 1, meaning that x is 0 and y is 1. So let's go ahead and plug that in and solve for our constant c. I will also mention sometimes, well, yeah, like actually with this problem here, it would not have been a good idea to have tried to solve for c right away. Most of the time, it's good to kind of solve for y and not figure out what your constant is until like close to the very end of solving for y. Here, that's not really an option. We can't solve for y. Y plus natural log of y, we're stuck, right? This is an unsolvable system, right? We can't actually isolate y. So we're just going to do what we can, and we're going to solve for the constant c. So plugging in 0 for x and 1 for y, I get 1 plus the natural log of 1 equals 0 plus 0 plus c. So c is going to equal 1 plus 0, so c is equal to 1. So then our final solution here is y plus the natural log of, do I need the absolute value? Probably not. Y plus natural log of y equals negative x cosine of x plus sine of x plus 1. And that's all we can do. So if you have, what's what I'm looking for? If you have a differential equation where after you integrate both sides, you've got multiple instances of y, it's most likely that you're not going to be able to solve for y, unless it's very specific, like you could help, where it's easy. Most of the time, right, you're stuck. Like if you have y plus e to the y plus natural log of y, there's nothing else you can do, which is okay. It's something to be aware of. Okay, let's look at some more examples. Let's look at some different, let's use some different variables. Let's look at something like, but not exactly. I'm sorry, 1 second. Let's look at this one. Let's look at, this is number 18 from the same section 7.4. dl dt is equal to k times L squared times the natural log of t, where L of 1 is equal to negative 1. So that means when t is equal to 1, L is equal to negative 1. Okay. So t and L are variables. K is just a constant. So again, we're going to separate. We're going to bring the L squared over to the left the only way we can with division. Or I guess if you wanted, you could say you're multiplying both sides by 1 over L squared. Same idea. I'm dividing by L squared. I get 1 over L squared dl equal to k natural log of t dt. And then we're going to integrate both sides. And the k is a constant, might as well put it out in front. Right. Okay, a couple things. First, to integrate this, let's rewrite it as L to the minus second. And to integrate the natural log of t, I do think it might be worth your while to memorize the integral of the natural log of x or the natural log of whatever your variable is. But you probably don't remember it yet, which is fine. To integrate the natural log of t, or the natural log of x, you have to use integration by parts. So the only choice we have here is to let u equal the natural log of t. And then dv is what's left, which is just dt. Du, the derivative of natural log of t, is 1 over t dt. And v is equal to the antiderivative dt, which is just t. So here's what we've got so far. We've got k times ultraviolet super Vuvu. So t times natural log of t minus the integral of t times 1 over t dt. Okay. Integral of L to the negative second is L to the negative first divided by negative 1. And then I get k times t natural log of t. Now look at this. T times 1 over t is just 1. And the integral of 1 is just t. So this is 1. And the integral of 1 is t plus c. Okay. So now I'm going to rewrite this so it makes more sense. L to the negative 1 is 1 over L. So I'm going to write this as 1 over negative 1 times L. But then dividing by negative 1 is the same as multiplying by negative 1. So I'm just going to write it as negative out in front. Okay. So 2 things. Thing 1, we have to take the reciprocal of both sides. So to solve this, I'm going to say, okay, the reciprocal of this is just negative L. The reciprocal of this is 1 over all of it. Oh, I should stop. I should maybe stop. Sorry, yeah, so good point. Before I do this, so this might be the moment where it makes sense to solve for C. It might not be. Maybe I'm jumping the gun, but I see here that C is kind of, out there on its own. So I could try and plug it, figure out the constants. And actually, I should double check one thing here. Yeah, okay. So if I solve for C right now, let's do it in a different color. I'm going to, let's see, I'm going to plug in negative 1 for L and 1 for T. So I'm going to get negative 1 over negative 1. So that's going to be 1 equal to K times 1 times natural log of 1 is 1 times 0 minus 1 plus C. So solving for C, divide both sides by K. 1 over K equals negative 1 plus C. So C equals 1 plus 1 over K. And yeah, C is in terms of the other constant that was already in the integral or the differential equation to start with. It's not very nice, but it is what it is. So that's what's going to go in right there. 1 plus 1 over K. So then we flip both sides and we get negative L equal to 1 over K times T natural log of T minus T plus 1 over K. And then finally, multiply both sides by negative 1 to get L equal to negative 1 over K times all that garbage. Questions about this? Yeah, the next one looks dumb, so we're not going to do that one. Yeah. You guys want to go with partial fractions? We don't have to, but we can. Let me grab times 234. Okay. Okay, partial fractions it is. Somebody said yes. I won't out them. Somebody said yes, which is fine. I'm always in for the yes. So let's do this one. You should try to make sure that you feel comfortable with any sort of notation, meaning, right, someone's going to write dy dt, dy dx, dn dt, right, d whatever. Yeah, so let's look at this one. Find the function f such that f prime of x is equal to f of x times 1 minus f of x. You could, if you wanted to, you could just replace f with y, right? If that made you more comfortable, you could write y prime equals y times 1 minus 1. That would also be perfectly acceptable. I'm not going to do that just so, right? I can do it this way. So I'm going to write this as, I'm going to try to make my life a tiny bit easier. I'm going to write f prime of x as df dx. And I'm going to write my f of x as just f, right? So just like you could write y of x as just y, f of x can be just f times 1 minus f. I will point out, just because it seems worth mentioning, this is an autonomous differential equation, right? Because the derivative is only depending on the function itself, not the independent variable. That's called autonomous. Again, not that important. So to solve this, all these things have to come to the left. I want to point out also, there's nothing else you can really do with this, right? Like, I mean, you could multiply it out and say it's f minus f squared, but there's no way, like, once you've got a factor of 1 minus f, you're kind of stuck with it. You can't, like, break it apart. In fact, like, or even just pretend for a second, let's say my differential equation was, you know, like dy dx equal to 4 minus y. There's no way you can separate the y from the 4. You have to divide by all of this, because division and multiplication are the only things we're allowed to do if we are separating variables. I'm going to say it 1,000 times because it's true. So the only way to get this over to this side is to divide by 4 minus y. The only way to get this stuff over to this side is to divide by f times 1 minus f. So I'm going to have df over f times 1 minus f. On the right-hand side, I'm going to have just good old dx. Or if you prefer, 1 times dx. That's also fine. You could write this as 1 over, then say it's df here. And we're going to integrate both sides. Okay, the right-hand side is super easy. It's just x plus c. It's going to be x plus c. The left-hand side is where we have to use partial fractions, right? You can see, hopefully, that we have a rational function. The degree on top is 0. The degree on the bottom is 2. So the degree on top is smaller. And the bottom factors. That means partial fractions. So let's do the partial fractions part on the other side. So we don't have to do it on this side. I'll try and get a quiz posted up later today as well. I might make it due on Tuesday instead of Monday since there's no class on Monday. But let's do this partial fraction. So we're trying to write 1 over f times 1 minus f. Was that right? Yes. Okay. So we're going to write this as a over f plus b over 1 minus f. We're going to multiply both sides by the common denominator. So 1 on that side, a times 1 minus f plus b times f. Just to make sure everyone is cool with that step. All right, all I did was multiply both sides by f times 1 minus f. Okay. I like to use the convenient values method, meaning I'm going to let f equal 1. If f is 1, I get 1 equal to a times 0 plus b times 1. So b equals 1. Let f equal 0. So then I get 1 equal to 1, a times 1 plus b times 0. So a is also 1. How convenient. So that means that 1 over f times 1 minus f is equal to a over f plus b over 1 minus f, which is 1 over f plus plus 1 over 1 minus f. And then since we've got the room, let's go ahead and do the integration. The integral of this is the integral of that, df. The integral of 1 over f is the natural log of the absolute value of f. The integral of 1 over 1 minus f, we have to be a little extra careful here. It's not quite the natural log of 1 minus f. Sorry, absolute value of 1 minus f. Right, and the reason is because if you took the derivative of this, you'd have to use the chain rule. And the derivative of the natural log of 1 minus f is 1 over 1 minus f times the derivative of 1 minus f, which is negative 1. We don't have a negative 1 there, so we need to change the sign so that we do. So, right, whenever you're integrating something, you've got like a multiple of your variable, you usually end up dividing by that multiple. So here we're getting the natural log of the absolute value of 1 minus f divided by negative 1, which just comes out in front as minus 1. In a similar way, right, just so everybody is super clear, the integral of like 1 over 3 plus 4x dx would be the natural log of the absolute value of 3 plus 4x divided by 4. Right, the coefficient of x in this case. All right, and then we probably want to put these together. I don't know, maybe I feel like I want to put these together as the natural log of the absolute value of f over 1 minus f. Probably not required, but it seems nice, so why not do it? Okay, back to the other side. So that means we've got that the natural log of f over 1 minus f is equal to x plus c. And I think this is an instance of, since we're able to put these together in one logarithm, I feel like we might actually be able to solve this. Yeah, we totally can. It's kind of fun. So this kind of thing comes up not infrequently, so you should see it at least once. So let's solve it. So we're going to get e to the, so in fact, right, the e to the this, e to the that. Okay, I'm going to make some shortcuts here. So e to the natural log of f over 1 minus f, I'm going to drop the absolute values and say I've got f over 1 minus f. And e to the x plus c, I'm going to write as k times e to the x, because it's e to the x times e to the c, and e to the c is a new constant. We call it k. And this one, so most of the time, it's true that when you have multiple, like, if you're trying to solve for f or trying to solve for y, if you have multiple f's or multiple y's, you usually can't solve it. This is an exception. We can solve this. Let me go to the other side. Yeah. So there's a couple different ways you can try attacking this. I feel like my favorite preferred way is to cross multiply. So f over 1 minus f equals k e to the x. Right. And then I'm going to cross multiply, or just multiply both sides by 1 minus f. So f equals 1 minus f times k e to the x. Distribute. F equals k e to the x minus f times k e to the x. Add this over to the other side. So f plus f k e to the x equals k e to the x. Factor out the f. And finally divide by this. So that f of x is equal to k e to the x divided by 1 plus k e to the x. Kind of cool. And we had an initial condition. I forgot what it was. Sure. The solutions I'm looking at look a little different than this because they did a slightly different thing. That's fine. Initial condition, sure. Let's say our initial condition was f of 0 equals 1/2. F of 0 equals 1/2. Then I'm going to get, let's see, so I'm plugging in 0 for x. So we get k e to the 0 over 1 plus k e to the 0 equals 1/2. It might have been easier to solve for this somewhere else if I had thought it. Right. So yes, it would have been easier to solve for it somewhere else, but I didn't say it until the end, so we didn't do it. It's probably easier to solve for it like right here, maybe. Whatever. We can still do it. So I've got k over 1 plus k equals 1/2. So let's see, cross multiply. 2k equals 1 plus k. Subtract a k and you get k equal to 1. So my actual final answer would be e to the x over 1 plus e to the x. Some people might write this differently. Some people might divide the top and bottom by e to the x and write it as 1 over 1 divided by e to the x is e to the negative x plus 1. That is also a valid way of writing the solution here. If you can see the negative symbol on my x, I feel like you can't. Okay. That one looks crazy. Sure. Okay, I think we should do a tank problem. And then if you guys want, we can talk about that tumor problem after we do a tank problem. The tumor problem's a little bonkers. But let's do a tank problem. Tank problems actually, so most tank problems we encounter, right, you're gonna have something in a tank with some concentration, and then you're gonna be adding in some concentration per minute, right? Like, so you're going to be adding in alcohol with a certain concentration at 5 gallons per minute, for example, and you're going to be draining out at the same volume per minute. However, you can also have tank problems where the volume going in is different than the volume going out. If you have a volume going in at like 6 gallons per minute and a volume going out at like 7 gallons per minute. That problem is a little bit different to set up. It's pretty much the same, but the difference is that particular type of tank problem ends up being a different type of differential equation. It ends up being a first order linear differential equation. So if we talk about first order linears, we will definitely do some tank problems that are a little bit even crazier than the ones you did in class. But let's do this one that is not. So just recognize if the rate in and the rate out are the same, it's a fairly straightforward, not that, right? They're still pretty challenging, but it's a regular separable differential equation. Whereas if the rate in and the rate out are different, it's going to be a first order linear differential equation. So let's look at this example. So a tank contains 1,000 liters of brine. And typically when I'm doing this kind of tank problem, I like to just draw a picture. So I've got 1,000 liters of brine in my tank. Yeah, briny, salty. Where's my blue pens? I've got some blue pens here. I got 1,000 liters of brine in the tank. 1,000 liters of brine. And with 15 kilograms of salt. 15 kilograms of salt dissolved. And then here's what we're doing. We are adding pure water to the tank. So we're adding water. Well, that's not, I kind of didn't quite, but usually like an arrow going. And so we're putting in water at, what's the rate we've got it going in at? 10 liters per minute. And we're draining it also at 10 liters per minute. And the question is, how much salt is in the tank after 10 minutes? Okay, so we're going to set up a differential equation for the rate of change of the amount of salt. So I should point out, when you're doing these differential equations for like these solutions with percentages of things or whatever, you always want to be thinking about the amount of stuff, not the like percentage of alcohol, for example, in the problem she did. So right, you want to be setting your equation for the amount of alcohol, not the percentage of alcohol. This problem doesn't have that issue, right? You're told there's 15 kilograms of salt, but if I had said like the brine was 1.5% salt, then we would have to multiply 1.5 times 1,000 to get 15, whatever. But okay, so we want to set up a differential equation for the amount of salt. So A of T equals the amount of whatever, salt in this case, at time T. And the differential equation, I'm always thinking about it as the rate that salt is going in minus the rate that salt is going out. It's always how I'm setting up these kind of tank problems, or I think she called them, oh gosh, there was a word, I wrote it down even. And, she called them compartment models, yeah. Stuff goes in, stuff goes out. So the rate in, how much salt's going in? 0, right? We're putting in pure water. Often people write this as, so the rate in is 10 liters per minute times the concentration of salt, which is 0 kilograms per liter. So the rate in is 0, which makes sense, right? If you're adding pure water, you're not putting any salt in the system. Minus the rate out. So the rate out is always the challenging part, right? Because the rate out is how fast it's going out, 10 liters per minute, times the concentration. So the concentration going in is 0 kilograms per liter. The concentration going out is, well, it depends, right? In the beginning, the concentration is 15 kilograms of salt per 1,000 liters of water. But as time goes on, the amount of salt is going to change. And so the way we write the rate out, is that the concentration going out. It's going to be the amount of salt in the tank divided by how much volume is in the tank, which is always going to be 1,000 liters. This is the key part to make sure you get right. When you're doing the rate out, it's always the amount of stuff in the tank divided by, when you're doing the concentration of the stuff that's going out. It's always the amount of stuff in the tank divided by how much the tank holds. Okay, so this is a differential equation. It's actually not a terrible one. We've got dA dt equal to, 10 over 1,000 reduces to 1 over 100. So I've got A over 100. And you could say it's, if you really wanted to, kilograms per minute, right? Because the amount of salt measured in kilograms. We don't need the units though, but it is nice to think about, the liters here do cancel and the units actually make sense. If you're talking about the amount of salt and how it's changing in kilograms per minute. Let's solve the differential equation. So I need A's on the left, T's on the right. So I need 1 over A dA equal to 1 over 100 dt. If you wanted to, you could put the 100 over here, but it's pretty typical standard practice to leave the constant thing on the side that is the independent variable on the right. So typically you leave that over there. Integrate both sides. So you get the natural log of the absolute value of A equals 1 over 100 times T, or T over 100 plus C. And now is not our moment to solve for C. We could, right? We know that at time 0, the amount of salt there is 15 kilograms. We could plug in 15 for A and 0 for T and get that C was equal to the natural log of 15. I don't want to do that. I don't want to carry that with me the whole way where I can make it easier on myself to do something different. So let's solve that equation. So I've got the natural log of A equal to T over 100 plus C. We're going to rewrite this as e to the natural log of A equals e to the stuff. This is going to be A equal to, remember what this is going to be, it's going to be K times e to the T over 100. And now is your moment to solve for your constant K. I know that A of 0 is 15. So plug in 15 for A and 0 for T. And oh, look, that's super great. K is just 15. That's a lot better, I think, than doing something else. So K equals 15. So our differential equation is, I feel like I might have made a mistake. I'm going to double check. I did make a mistake. I knew I made a silly mistake. So I did. It's a small mistake. It's not a huge deal. Well, actually, let's finish the problem and then go back and let me tell you how I know I made a mistake. So let's pretend like this is right. Fixing it's not going to be terrible, so I'm not too worried about it. So let's say we have A of T equal to 15 e to the T over 100. And then the question was, how much salt is there after 20 minutes? So if I plug in 20, I get 15 e to the 20 over 100. Looking at that doesn't actually let me know that I've made an error, but if I plug it into a calculator, let's see what happens. E to the 20 over 100 is 1.22 times 15 is approximately 18. Well, that's a problem. I added pure water to the system that started with 15 kilograms of salt, and I ended up getting 18 kilograms of salt after 20 minutes. That seems wrong. So it's really important to make sure you understand the context of the problem. It'll help you catch errors that you made. What I was actually really thinking about was that I know that as T gets really, really large here, this number gets super large. which means the amount of salt as time goes on would get more and more and more and more and more without bound. That also seems very unlikely. Here's the mistake I made. I lost a minus sign right there, right? That should have been 0 minus a over 100. So there should have been a minus sign there. There should have been a minus sign here. There should have been a minus t over 100 plus c. There should have been a minus t there, a minus t there. So our answer really was a of t equals 15e to the negative t over 100, which makes more sense because then as t gets larger, the power gets more negative and the value gets smaller. So if I plug in negative, or if I plug in 20 into that, I'm going to end up getting 15 times e to the negative 0.2, which is going to be about 12.2. Okay, so here's another interesting question to ask. What happens as time goes on forever? What does the behavior of this system do as we let time just go on and on and on? Well, in this case, as time goes on and on and on, or I should say, right, as we take the limit as t goes to infinity, we get 15e to the negative t over 100. Well, as t goes to infinity, you get e to the negative infinity, which is going to go to 0. So if you let time go on forever and ever and ever, eventually the concentration of salt or the amount of salt in the tank will be 0. Here is an excellent thing to know for these tank problems. If you let time go on forever and ever and ever, the concentration of whatever stuff in the tank gets closer and closer and closer to the concentration of what's being put into the tank. So since I'm putting in pure water with a concentration of 0 kilograms of salt per liter, eventually the tank gets closer and closer to having 0 kilograms of salt per liter.